So today we're going to talk about like first part of the history before the Renaissance. And then before the Renaissance, it was everything was pretty much not as scientific as we hoped for. Okay, so um, in order to understand how Newton got his gravitational theory or universal gravitation, there were a lot of contributions that helped Newton formulate his theory of gravity, right? And the formula that helps understand, you know, what causes planet to move around the sun and what causes the moon to go around the planet and so on. So to appreciate all that, let's see how we got up to where we are, starting from ancient Greek model when people in the ancient Greeks thought Earth was flat, and today people believe Earth is flat too. All these flat earthers are all over the globe. You know, so it's going to be interesting how they're going to present that. But back then, they didn't really know any idea how, Earth could be. They couldn't conceive it. But they did realize if they actually go outside at night and they take a look at a star, let's say, if they were to find a star where they would, like on the horizon, okay, so if you are at a horizon at evening, okay, and you're like sitting around with your friends and they see a star, let's say, up in the sky, okay, so you're watching that star with your friends. So here's your eyeball right here. You're watching that, and you're watching that star, okay, and then you want to put some kind of a fixed point so that you know. So I would put a stick in the ground here like this, and I would put another stick in the ground like so. And then if I were to look through those two, and then like aim at it, I will be able to see exactly where that star is located from my fixed position. Maybe I should put my eyeball a little bit further back, so like right here. So if I were to, look at that star, and then I would be able to see that star lining up with these two sticks that I planted into the ground. An hour later, when you come out and you take a look at it from the same spot through these two sticks, that same star that was up there pretty much moved 15 degrees, right? So 15 degrees from the fixed position where you had previously to where it is now. So they knew the stars actually rotated 15 degrees per hour, roughly. Every hour, stars rotated 15 degrees. There was only one star that didn't rotate, and that's the pole star, which is the North Star. And everybody pretty much used that star to navigate, but that will not rotate for some reason. Okay? They also realized, every day when sun sets along the horizon, it would actually move, right? Like sun would set, like, let's say a certain spot every one evening. And so you put two sticks down. Day later, it shifts, 1 degree every day until December 21st. At December 21st, it sets same spot 3 days in a row. And then it starts to shift back the other way until the summer solstice when it sets in the same spot. Now, during this winter solstice, when it sets in the same spot, the days get shorter and shorter and nights get longer and longer. So people thought, oh my God, if this continues, we're not going to have any sun, you know? So in other cultures, they would actually do some, sacrifices, But in Northern Hemisphere, they realized, you know what? When sun sets here 3 times, they know it's going to get longer days from that point on. So what they did was they would like construct this like huge lapidarious structures, like huge stones, so that whenever the sun sets right through this crack, they know it is time to party. And they would party hard because they would party for 3 days and 3 nights. They would bring the biggest Yule log and burn it, for 3 days, and they would just like party up because they know the days are going to get longer. And here too, somewhere here when it sets here, they knew it's going to get dark from that point on, and so on. And when sun sets here, they knew they had to either harvest or they need to plant. They need to plant, crops. So they created a calendar system for human survival. All right. All right. So sun's path is called ecliptic, right? And if the plane of the sun is tilted at 23 degrees, so they already knew the tilt of the planet already. From the equatorial plane, this accounts for why the sun is high in the summer and low in the winter. But this is only true for the northern hemisphere, obviously. Okay. Then, around 500 to 582 to 500 BC, or BCE, if you want to be historically correct or politically correct, Pythagoras still believed the Earth was the center of the universe. Okay. However, Earth was spherical. It wasn't a flat postage stamp like this, but he realized it was a sphere. And he realized that by watching lunar eclipse. And when he watches lunar eclipse, he knew the Earth was casting shadow on the surface of the moon. And when it does that, it was a spherical shadow. So if this is the moon, right? The shadow it casted was, it was like spherical shadow rather than if it was a flat Earth, and during the lunar eclipse, you would have a shadow that looks like a pizza on the side. And that's not happening. So he observed this. That's why he knew the Earth had to be a spherical object. All right. He also noticed that when you observe the stars rotating 15 degrees every hour, they all rotated synchronously, right? Synchronous to all the other stars. They all rotated together, except there were some stars that would not go with the same direction as the other stars or at the same speed as the other stars. And they were called the wandering stars or the wanderers. Well, now we know it as planets, right? Because there weren't stars. And these wandering stars would actually rotate with their other stars, but at different speeds. But sometimes these stars would actually go backwards. And then you would actually and then realize, what, they're going backwards, and so they make a turn again, they go forward again. And this is called, epicycle and retrograde. And these were, they couldn't explain it. They couldn't explain why it does that, Now somebody asked me like, well, I don't think that's true because you can't see these things go like that in that evening sky, No, you don't see that in 30 seconds. You see this in like several weeks or 2 days, or you have to see this for more than 2 weeks in order to see the pattern of this thing. Okay, you don't see a planet going like that. No, right? So it's important to understand that these observations take long periods of time to record and to analyze. Okay. The epicycle and retrograde is observed, and they decide to give those wandering stars planets. Okay, and they named it after Greek gods. Then in Hellenistic age, right, which is Alexander the Great, pretty much conquered all the known world back then. There lived a librarian of the great Library of Alexandria. His name was Eratosthenes. Now, Eratosthenes, he would actually put all the books in the proper place and categorize the books and different things and different shelves. But in order to categorize those books, he had to read them. Before he read them, obviously, they had scribes that transcribed all the books from different parts of the world that came into Alexandria, and they turned it into many different languages, and they categorized it. But in order to categorize, he had to read them. And one incident, there was one book that actually represented, well, recorded that at Syene in summer solstice, June 21st, the wells in Syene would cast no shadows at the bottom of the well. The sun would be directly above, and you would not see the shadow on the bottom of the well. That means the sun was exactly above. Well, most people would say, oh, that doesn't, okay, so what? And then they'll just move on. But Aristophanes says, wait a minute. Where I live in Alexandria, there's definitely a shadow at June 21st, according to our calendar, right? So that's kind of odd. But why would it cast shadow in Alexandria? But why wouldn't it cast shadow at Syene? So he went to investigate, right? I'm sure it took more than several years to really get this thing right, because he would have to measure it here, he would have to measure it here, and then he had to do it again just to make sure it wasn't a fluke, right? So it wasn't something that's instantaneous. However, he did realize at Alexandria that obelisk that sticks up would cast a shadow on the ground. The shadow on the ground will be short, and when he measures that shadow with this angle right here, it came out to be 7.5 degrees roughly. So if he were to extend this thing all the way out and extend this straight out the other way in Syene, this arc is also 7.5 degrees, because if we have transversal cutting through two parallel lines, the alternate interior angles are congruent. And that was pretty much proven by Pythagoras 600-700 years ago. So here, he realized this can only happen if the Earth's surface was curved. And when it curves, these two lines should meet at the center. So if he were to draw out a circle and measure out this arc length, which was very well-traveled business route from Syene to Alexandria, and he actually had his assistants painstakingly measure out the distance from Syene to Alexandria, and it was about 5,000 stadia. And 5,000 stadia is about approximately 500 miles. And with that knowledge, he calculated the circumference of the Earth 250 years before Christ was walking around the Earth. Right? 250 years BC, he calculated the circumference of the Earth, and it was circular. It was spherical, you know? And we still use that 24,000 miles. It's pretty amazing how accurate he was. Okay? So, what a contribution to humanity. Then Aristarchus of Samos, he tried to figure out the diameter of the moon and the diameter of the sun and the distance, so on, using all these different geometric identities. Right? And he also said, you know what? He believed, Aristarchus believed that our solar system or our universe was not centered at the Earth, but the sun was actually the center of the universe. Okay? So he introduced the heliocentric model, where he put the sun at the center of our known universe, and all the planets and wandering stars and all the other stars revolved around the sun. Okay. Aristarchus also proposed that while the Earth travels around the sun, it spins on its axis. That's sick, if you think about it, right? That's sick. He had that sort of figured out way before 250 BC. Okay. It won't be until like 1,800 years later that Nicholas Copernicus or Nikolai Copernic would reinvent this theory and then reintroduce it. All right, so Aristarchus' Copernican model explains the epicycle and retrograde very beautifully, and he was, however, afraid that he would get burned at the stakes, so he held on to his discoveries until the deathbed. And he published his book, waited and waited, and he got his first copy on his deathbed before he died. They believe Copernicus was well connected. That's why. Hipparchus is another interesting character. Now, Hipparchus, he's known as the father of trigonometry. Okay, and he actually recalculated Aristarchus's distance to the moon and distance to the sun and diameter of the moon and diameter of the sun. He got the moon pretty correct, but the sun, he had no idea how big sun was. I mean, like, he had no clue how huge the sun was. And he got that pretty wrong. The size of the sun and the distance of the sun was almost incalculable at those times. But he did get very close with the moon's measurement. And here's another thing that is kind of interesting. He also realized the Earth axis, it precesses, which means it sort of like wobbles. So if this were the Earth axis and Earth spins around this like this all the time, well, this axis actually wobbles around like this in a circle as it spins. But this wobble, that one circle, one wobble here like this, took 25,000 years. So depending on where the axis was pointing, it would be pointing towards a different constellation. And that's how we get the 12th constellation. So during like the pyramid time, and when they were building the Sphinx, they believed the axis was pointing towards Leo constellation, the lion. During Moses' time, they believe when they were building pyramids, Moses' time, they were worshiping bull, the sacred cow. So age of Taurus was when the axis was. And when Jesus was born, it was Pisces, which is fish. So the Christianity is symbolized with fish. Now we are at the Aquarius, which is the water. And so every 2,000, give or take a couple hundred years, we have a new constellation, right? So because of that wobble of precession. Okay. I thought that's kind of cool. Much later, right? So this is like 150 after, right? Jesus. So everybody thought AD was after death, but it's actually Annus Dei, which means like year of the Lord. So same thing, I guess, right? So it should be CE for those politically correct, Common Era, right? So 150 years at Common Era, right? Ptolemy, right, decided to create his own system where he put the Earth back on the center of the universe again, right? Obviously, he's wrong because center of the universe is not Earth, it's me, Mr. K. I am the center of the universe, right? So here, he created this elaborate system of how everything goes around the Earth and it spins around its own, orbit, and and they all go around the Earth basically. And people said, okay, that's fine. So he published this Armagist that pretty much represents what his system is. They used this Armagist as a church calendar, and church adopted this system, and they continue to believe it for more than 1,000 years. But they realized after several hundred years, things weren't lining up properly, so they had to make some corrections. And of course, Ptolemy's dead by now. And they were trying to figure out when the next Easter was going to come, but they couldn't calculate it because it was messed up. And they couldn't even calculate when the Christmas was and all the other stuff. So they had to like always make corrections, and it was kind of messy. But church didn't want to say they're wrong, so they just kept the system going. Okay. Then comes the history of the world, part 2. Notice the time, right? From Ptolemy, which is 150 years, to 1,400 or 1,500 years, right? So Nicholas Copernicus, Polish monk, right, reinvented Aristarchus' model of the heliocentric frame of reference of our solar system. So he said, let's put the sun back in the center. And he knew that church had adopted Ptolemy's model as part of its dogma, and therefore would not accept this radical change. And people thought he was nuts, you know. I mean, actually, if you were to introduce that to the world, he would have gotten like well, not crucified, but he would have gotten burnt at the stake, actually, live, right? He intentionally delayed the publication of his great book, De Revolutionibus Orbium Coelestium, until the year he died in 1543. So he got his first copy on his deathbed. Okay. Now, about 3 years later, Tycho Brahe came to the world, and he was Danish nobleman, so he lived in Denmark. Right? He was a very flamboyant person. He had pet elk, very rich, right? Very spoiled, more rich than mainline, right? And he had these systems where these protractors and sextants were like huge, like 20-footers, that can actually measure the locations and positions of stars so precisely. He had the best data with the naked eye observation. So he and Johannes Kepler were the last naked eye astronomers, which means they did not use any magnification devices. He just used eyes, right? And he collected all these, well, he probably didn't collect it. He probably had his servants do it, right? And all these workers do it, but he took all the credit, obviously, right? And he had all these data collecting basically all the wandering stars, the planets, okay? Then in 1564 to 1643, Galileo Galilei. We're going to talk about this guy a lot more. We're going to actually watch a video of this guy. He's pretty intense. This guy's pretty intense. All right. So supports Copernican model and uses his newly invented telescope to verify the model they observed in the phases. Johannes Kepler, also known as the wandering mathematician, right? He was German. And Kepler had the mathematical talent to use Tycho Brahe's data and put it to good use. However, it is unclear if Kepler was given Tycho's data or whether he stole it. Right? In either case, he used it well, and rest is history. There's like a rumor, right? Tycho Brahe died because it was very unpolite to stand up from the dinner table and go to the bathroom to relieve himself. So, as being a nobleman, he stayed at the dinner table instead of going to the bathroom. His bladder bursted, and he died a very painful death because his bladder bursted. That's only a rumor. However, they exhumed his body recently, a few years ago, to find out what really happened to Tycho Brahe. And guess what? They found arsenic in his hair samples and fingernails. So he must have been poisoned. We cannot tell who poisoned the person. I mean, like, we don't know who poisoned him. But there's some suspicion, right, that he's poisoned because of his scientific data. I'm not going to point fingers who did it, but somebody poisoned him and somebody killed him so they can get his stuff. Well, anyway, after his death, the Brahe family constantly sued Kepler for their data back. And Kepler say, yeah, I'll give it to you. I'll give it back. And he would give back like Jupiter, and maybe some Venus and other planets, but he kept one planet to himself, the observations of Mars. If he did not work out the orbit of Mars, he would have probably thought all planets moved in a circle because it was very, very close to a circular orbit. Mars was the only planet that had enough eccentricity to figure out that it wasn't a perfect circle. It was slightly off, and it wasn't a circle. Matter of fact, it was an ellipse. Right? So these three laws come into play. His first law of motion, right, was all planets travel in an elliptical path where the sun is in one of the foci. In an ellipse, there are two foci, right? And if you were to actually put a peg where the two foci should be, and you get a string, and you put the string around the two foci and get a pencil and trace it around, you'll get a nice ellipse. Okay? This drawing shows a very large eccentricity of ellipse. So it looks so flat, like it's flatter than an egg. However, in true orbit for planets, the eccentricity is so small, the foci are almost right next to each other. Matter of fact, some foci for the other planets, the foci are within the sun. That's how close the foci are. Right? So most planets are quasi-circular orbit. Mars is the only one that's recognizably ellipse, only mathematically. Right? So his first law is all planets move in an elliptical path where the sun is one of the focal points. This is very exaggerated, people. Second law of motion is the line joining the sun and the planet, right, sweeps over equal areas in equal time. So what does that mean? If the planet is moving in an elliptical path, on an elliptical orbit, right, when the planet moves from one point to another, depending on where this planet is, if it's further away from the sun, it would sweep out an equal area of this area right here. Let's say it takes 30 days to go from here to here. It has to sweep out exact same amount of area in 30 days when it's closer to the sun. So this area swept out has to be exactly the same area as this, which takes 30 days for both of this. So when it's closer to the sun, the planet has to travel much, much faster to sweep out the equal area in 30 days than if it's further away from the sun. All right? That's what the new Kepler's second law states. The third law, which is kind of mathy, but this is important. This is what contributes to Newton's universal law of gravitation. The third law states, the squares of the periods of the planet's motions are proportional to the cubes of the semi-major axis of their elliptical paths. That is, c cubed. Now this c cubed is semi-major axis is from the center of the ellipse to the longer part of the axis. Right? So this is the major axis, semi-major axis. Right? This distance cubed divided by the period of the planet squared is constant for all planets. That is mind-blowing. Absolutely mind-blowing. Okay? That means if I know one or the other of one planet, you could calculate the other. You could observe the period of the planet. You could tell how many Earth days it takes for a planet to go around the sun by careful observation. That means if you know that, you could compare that to Earth, how far that planet is away from the sun, just by this formula. Okay? So, this ratio helps astronomers calculate the distance of the planets from the sun. Okay? So since the sun is almost at the center, which is the foci are very close to each other, right? The distance c is going to be basically same as the radial distance. All right. So this, when you use this ratio can be used to calculate. So for example, let's say the distance from the center of the sun to Earth, we call it 1 AU, astronomical unit. And we know the period of the Earth around the sun, that's 1 Earth year. If we know how long it takes for Jupiter to travel around the sun, we can calculate the distance of Jupiter from the center of the sun to Jupiter in AU units. Okay? So this ratio is very important. He also recognized that this ratio is constant, which means that c cubed over period squared is equal to, well, this came a lot later, but it is g times the mass of the whatever the central mass is. Divide that by 4 pi squared. When you use this formula, you must use period in seconds, and you must use distance in meters. The reasoning is of this constant g. We'll talk about this more later. So this mass here is the mass of the central mass, which means if the Earth is going around the sun, this mass is sun's mass. If you're looking at moon going around the Earth, this mass is the mass of the Earth, right? The central mass. So we'll talk about this more in detail. Right? Notice this is constant. It's just a numerical value. Because mass is going to stay constant. Pi is constant. This g is universal gravitation constant. So they're all numbers. Okay? If you rearrange this, you could say the period squared is equal to, right, 4 pi squared over gm times c cubed. All right? So this is Kepler's third law. During that time, Galileo used his telescope. Galileo never discovered, I mean, he never invented it. He improvised it and improved it. Telescope's been a novelty toy for like, some created by some Dutch glass lens maker. And he discovered four moons of Jupiter, and he put the church, science, everything upside down on its head. And he is the most important figure in studying physics. So, whew, I'm going to let you use this, okay? For now, what you need to do is you need to just use just this. Just this. This and this are the exact same equations. Okay? These are exact same. They're just arranged differently. Your homework is to do the first page right here of this Kepler's law worksheet. Okay, that's your homework. Easy stuff. Okay, so I'm going to go over that tomorrow. And I'm going to end the lecture here today. And we're going to learn about Galileo Galilei. All right?